Hello everyone, welcome to day 9 of graph theory. We're going to be talking about sorted edges, or its other known alias called the cheapest link. Alright, so this is another method that is designed to find a Hamiltonian circuit. Remember, a Hamiltonian circuit is a circuit that visits every single vertex exactly once and then returns home. Right, so you can start it like vertex A. You go and you visit every other vertex, and then you come home. You don't have to use all the edges, but you do have to visit all of the vertices. All right, and we've learned a few methods, or two methods for this so far. We learned about the brute force method, right? So brute force, which is where we actually go and find every single Hamiltonian circuit that exists in the graph, and then just simply choose the shortest one. We found that was a lot of work, and especially for larger graphs, was nearly impossible to manage. All right. The second method that we learned was the nearest neighbor algorithm, right? So we had the nearest neighbor algorithm. This one was really quick, right? It's what we would call efficient, but it was not optimal because it did not find the shortest route every single time, but it was quick and easy to use. So it was a lot easier to use than brute force, but brute force guaranteed you the shortest path, nearest neighbor didn't. All right, so we're going to talk about this is what we would call another heuristic algorithm today. So it's another algorithm. It doesn't guarantee you the shortest path, but it is something that is optimal. In other words, it's fast and efficient, something that we can use. Now, the nice thing about sorted edges is that it usually, not always, beats out nearest neighbor. In other words, it finds a more optimal path than nearest neighbor most of the time. Okay, so that's enough of the introduction. Here's the algorithm in itself, right? So this is the step-by-step, right? So we're going to go into a graph. We find the cheapest edge that is in the graph, and we simply add it to our circuit, okay? It doesn't matter where you start. You're going to end up with a circuit that uses your starting point vertex anyways. So you just go in there, you find the cheapest edge, highlight it, and then you would repeat step one, adding the next cheapest edge. No matter where it's at in the graph, you just go and you add it to your circuit, as long as it doesn't do one of the two things listed here. All right, so we do not want to add an edge that would create a circuit that does not contain all the vertices, right? Because we want to make sure we visit all of the cities. All right, so if we complete a circuit that does not include one of the cities, well, that defeats the purpose. All right, the other thing we don't want to do is we don't want to create a vertex with a degree of 3. All right, so every vertex, as we add edges to our circuit, should never exceed a degree of 2. And you'll see what that looks like as we go through it. All right, and we're just going to keep repeating this until a circuit that contains all the vertices is formed. All right, so let's look at an example, see how this works. Okay. For right now, ignore these things down here. We'll talk about those in just a minute. But let's go ahead and do sorted edges. So I'm going to grab a highlighter. I like highlighters for this particular algorithm. And you just go into the graph and you're going to find the cheapest edge, which is going to be from A to D here. That is the cheapest edge with a cost of 1. So I'm just going to highlight that edge, and you can see this is now part of our circuit. Right now, what we have in our circuit is a path that travels from A to D. Okay, the next cheapest edge in our graph here is this one from A to C, which has a cost of 2. So I'm going to add that one. Right, I'm going to add that one to my circuit. So this is my circuit so far. Okay, this is where I can travel so far. Notice that vertex A currently has a degree of 2, right? If I take the two edges that I have here, they both lead into A. So this has a degree of 2. All right, C currently has a degree of 1. D currently has a degree of 1. All right, so then I'd go to the next cheapest edge, which is this one right here, A to B, which has a cost of 4. But if I were to add that edge to my circuit, all of a sudden vertex A would have a degree of 3. I would have 3 blue lines coming into vertex A, giving it a degree of 3. That we can't do. That's one of the things we said we would not do. All right, so we skip over AB. We go to the next cheapest edge, which is going to be DC. Okay, so here's DC. Now I'm going to go ahead and highlight it, but watch what happens here. If I highlight this, notice that I complete a circuit. Okay, so this is a completed circuit. It makes a loop. But this loop or this circuit does not include vertex B. We cannot do that. We have to have a circuit that includes all the vertices, so we have to skip over edge DC. Okay, so we cannot include edge DC. We have to go to the next cheapest edge. All right, so we skipped over 4, we skipped over 8. The next cheapest edge is this one here with 9 going from B to D, so we can see our circuit so far. And then we would go to the next cheapest edge, which would be the 13. And when I highlight the 13, that actually completes my circuit, right? So you can see your complete circuit here that travels through the graph, visiting each city exactly once. So this is the circuit that is produced by sorted edges, right? So if I'm writing this out, I have my pen here, if I'm writing this out, let's say I wanted to start at vertex A, I can go up here to A and say, okay, we start at A, then I go D, B, C, A, and I'll just write that out instead of D, B, C, A. There's my circuit starting and ending at A, and then I would add up my edges. So we got 1 plus 9, which is 10, 10 plus 13 is 23, 23 plus 2 is 25. So there's my circuit, there's its cost. So that is sorted edges, and I want to come down here and just talk about a couple of things. So we've actually seen this graph before. We did the same exact graph when we did brute force, so we know what the cheapest route is. It was A, B, D, C, A, which had a cost of 23. We know that is the optimal route. When we did this same graph with nearest neighbor, we got a route that cost 26. Now what we just did with sorted edges, we got a cost of 25, which slightly beat out the nearest neighbor algorithm. Now remember, sorted edges is not guaranteed to beat out nearest neighbor. It usually does. It's a loose mathematical term. It usually does. Most of the time it will. All right, and I put these in here just so you can think about situations that you want to avoid. So in this one, we added edge AB here, which created a vertex with a degree of 3. That you can't do. Here we completed the circuit that did not include vertex B, so this would be bad as well. This is okay, right, because none of the vertices have a degree of more than 3, and we don't have any completed circuits in this particular graph. So bad, bad, okay. All right, so this is just to kind of give you a visual to help you think about what you are allowed to do and what you're not allowed to do with sorted edges. Let's try another one. Okay, so this one says plan an efficient route using the sorted edges algorithm. So we're starting at home in Seattle. And remember, we're trying to find a Hamiltonian circuit. So we want to visit all of these cities and then return home to Seattle. Okay. I'm going to grab my highlighter again, and we're going to find the cheapest flight. Doesn't matter where it's at on the graph, we're just going to find the cheapest flight, and that looks like it's Seattle to LA. So I'm going to take that edge and I'm going to add it to my circuit. So this is now my current circuit, right? Whatever's blue is the current circuit that I have built so far. All right, then I go and I find the next cheapest flight, no matter where it's at on the graph, it does not matter. So the next cheapest flight is this 75, and I'm going to add that to my circuit. I know it's not a complete circuit yet. That's okay. It doesn't matter. Wherever the next cheapest edge is, that's what we're going to highlight. And it's okay to highlight it because we didn't create anything with a degree of 3 and we didn't complete any circuits. Okay, so we're good. Now the next cheapest flight would be the $85 flight going from Atlanta to Dallas. So I'm going to add that one to my circuit here. Okay, so there's my circuit so far. I have not created anything with a degree of 3, and I have not closed any loops or circuits, so we're good. The next cheapest flight after $85 is $100, so that would be here. And you start to see our circuit form. All right, so we go from $100 to the next cheapest flight. I'm just checking them here. So 120 is the next cheapest flight. So I'm going to add that one, and I just checked nothing is degree 3. I did complete a circuit. You notice I completed a circuit, but this is okay because this circuit includes all of the vertices. All right, so I'm going to grab my pen. I'm going to write my circuit. So we start at home in Seattle. And you can go either direction here. You can go around this way or you can go around this way. It's going to be the same circuit and give you the same cost. Okay, so we can go from Seattle to LA. LA to Chicago, to Atlanta, then from Atlanta to Dallas, and then from Dallas back home to Seattle. So this is my Hamiltonian circuit that I'm going to take to visit all of these cities, and then I need to add all of the costs here. So I need to find out how much this is going to cost me. So if I do 70 plus 100 plus 75 plus 85 plus 120, you should get a total cost of $450. Okay, so this would be our route using sorted edges. Let's do another one. This one we're going to do another comparison. So first we're going to do nearest neighbor, and then we're going to do sorted edges and see which one wins here. And in a lot of cases, since these are very easy to use, you'll see a lot of computer companies, a lot of software that will actually run both just to see if they can find a cheaper one using either one of these. So it's not uncommon, since they're both very low cost algorithms for a computer system to run. All right, they don't take a lot of processing power. All right, so here we go. I'm going to grab my highlighter and let's go nearest neighbor. Actually, we'll use, so nearest neighbor, we have to start at vertex A. And remember, nearest neighbor says choose the shortest path every single time, right? So the cheapest edge coming out of A is 2, right? So I'm going to add that. And then I like to write my circuit as I go. So we're going to go A to E. Right, and then from E, again, we have to choose the cheapest path. So we're going to choose this one going down here to C. That's going to be the 1. So I'm going to add C. I'll highlight that. Okay, go back to my pen. And then from C, again, we have to choose the cheapest path. That would be 4, but that takes me back to A. I've already visited A, so I can't go back there. So I'm going to choose the 6. So that takes me out to D. Go. So there's D. And then from D, I have to choose the shortest path, which will be the 2, but that takes me back to E, which I've already visited, so I have to go to B. There we go. And I've got that in there. Let me add B to my circuit. And then from B, I can't take the 3, it takes me back to E. I've already been there, so I have to go back home to A. So this is what my completed circuit looks like in this graph, and then I would finish that off here. Right? So A back to A. There's my result from nearest neighbor, and then I would add up those edges. I believe if you add up all of the edges here, you're going to get 21. Okay. Now, I'm going to start over, so I'm going to erase all this stuff off my graph here, and then I'm going to start over with, this time I'm going to do sorted edges. Okay, so I'll grab my highlighter, and again, it doesn't matter where you start, right? We just go and we find the cheapest edge that is in the graph for sorted edges. So we have a 1 here. Okay, so that gets added to my circuit. Now you guys might be thinking, the next cheapest edge is a 2. Right? So, and I have 2 2. So which one do I do? Technically, you're supposed to do both of them. All right. So pick a 2, and then continue on with cheapest link or sorted edges, and see what you get. Then go back and do it with the other 2. So I'm going to pick this one. I'm going to pick this 2. Right. So that would be the next cheapest edge. So then after the 2, the next cheapest edge would be the other 2. But if I selected that one, it would create a degree of 3 at edge E. So I can't select that one. I also cannot select the 3, right, which would be the next cheapest edge, because again, that would create a degree of 3 here at E. All right, so I go to the 4, which is the next cheapest edge. That one I can choose. All right, so I'm going to highlight the 4. There we go. And then the next cheapest edge after 4 would be the 5 up here, and the 5 is fine. I can choose that one. That's not going to create any degree of 3s, and it doesn't complete any circuits. The next cheapest edge is the 6. I cannot choose the 6. That would complete a circuit here that does not include all of the vertices. So I don't want that. So the next cheapest edge then becomes the 7. I can select that one. It does complete a circuit. Right, you see the circuit there that is completed, but it is a circuit that includes all of the edges, so that is okay. Okay, so here is with the first option, right? When I choose this 2, this is what I get from sorted edges. So I get A, C, E, D, B, A, and if I add those up, I get 19. Which is great because that beats out nearest neighbor, but I do need to go back. So I'm going to get rid of everything here. And I'm going to go back to where I made this decision to choose this 2 down here, and I'm going to choose this 2 instead and see if I get anything different. Okay, so now I choose that too. Okay, so the next cheapest edge would be this 2, which I can't use. Then the next cheapest edge would be this 3, which I can't use. Right, both of those would create a degree of 3 at vertex E. So the next cheapest edge would be the 4, but that completes a circuit right here, so I can't use that one either, so I got to go to the 5. Okay, so 5 would be here, and that's okay. The 6 would be the next cheapest edge. I can add that one. And then the 7 would be the next cheapest edge, and that's okay. That would complete my circuit, but that circuit would include all the vertices. Okay. So let's see what this edge does. All right, so we'd go A, E, C, and then we'd go D, B, A. And if you add up 2 plus 1 plus 6 plus 7 plus 5, you get 21. So this is the edge that we would pick. I know that was kind of annoying because we had the 2 2s there, but it could happen. You can get edges that have the same cost, and unfortunately the only easy way to settle that with sorted edges is just to run all the possibilities. So if you do have an edge that is like a duplicate lengthwise, just do them both. Pick one and run with it, then go back and pick the other and run with it and see which one produces the shorter route. All right, so last one. Let's do one more just to make sure we got this down. So we're going to do nearest neighbor and then sorted edges. So let's do nearest neighbor first. And so we're going to start at vertex A. So for vertex A, you've got to choose the shortest, right, every single time. So I'm going to choose the 1, right? So I'm going to go from A to B. And once I'm at B, I got to choose the shortest route. So we've got 5, 10, and 12. So 5 is going to be the one that I have to choose. So we're going to go to C. Once I'm at C, I've got to choose the shortest one. Well, unfortunately, the shortest one here takes me back to A, and that's no good. So then we've got 9, and we've got 7. So I got to choose the 7. Now I'm at D, so again, I got to choose the shortest one. So we've got 10, 14, and 3. So 3 is the cheapest one, which takes me to E. And once I'm at E, we've got 12, 9, and 11. So 9 takes me back to something I've already visited. So 11 is up next. And while 11 does take me back to something I visited, it completes my circuit, which is okay, right? Because the circuit that is completed includes all the cities. All right, so we have A, B, C, D, E, and then back to A. And then we would add up those outer edges. We got 1 plus 5 plus 7 plus 3 plus 11, and we get 27. Okay. So let's see if we can beat that with sorted edges. Let's see what we can do. Remember sorted edges, wherever it is in the graph, find that shortest route or find that shortest edge. So that's going to be the 1. Then find the next shortest edge. That's going to be the 2. So I'm going to add that one to my circuit. The next shortest edge would be the 3 down here, and I can go ahead and add that one. And the next shortest edge after 3 would be the 5. But if I include the 5, that would complete a circuit, so that's no good. The next shortest edge is the 7. And that one is okay. It didn't create anything with a degree of 3. So this one's degree 2, this one's degree 2, this one's degree 2, so we're good. All right, next shortest edge is the 9. I can't do that one. That would complete a circuit. Next one would be the 10. So that would be no good because that creates a degree of 3 here at D. So then I go to the 11. I can't use the 11. That would create a degree of 3 at A. So then we would go to the 12, and the 12 should be good. And that actually completes a circuit. All right, so A, B, E, D, C, A. So that completes a circuit, and that circuit is okay because it includes every single vertex. So we are done. All we have to do is write down that circuit. All right, so we'll start at A, and let's say we go from A to B. From B, we would travel down to E, E to D, D to C, and then C back to A. And then we would add up all those edges. So 1 plus 12 plus 3 plus 7 plus 2 is 25. And that beats out nearest neighbor again. All right, guys. Hopefully you found that useful. It's several examples with a lot of not a lot of, but some weird situations that might pop up as you explore this particular algorithm. Like I said, I hope you found it helpful. If you have any questions, make sure you let me know in the Zoom chat. I can walk you through one of these. Have a great day.